Okay, so welcome students, and we are discussing the circular dichroism and its application in biophysics research as well as biopharmaceuticals. So, today mostly I am going to discuss about molten globule like structure in the protein, but before that I just want to remind you what we discussed in the last class, the application of CD in biopharma, right. So, biopharma, especially in Indian biopharma, most of the people are working on biosimilars. So, they want to make the highly similar drug product which is like a highly similar respect to the already approved drug, which is we call it RLD, reference listed drug, right, and the patent is going to expire. So, they are all working on this to make a highly similar drug, right. So, and the issue is here, unlike a small generic drug which we take a like a often the small pill that we swallow, those does not require that much like a structural investigation, but biosimilars require lots of, because they do not have only primary structure, but also secondary structure, tertiary structure, quaternary structure. So, essentially manufacturer needs to show that their molecule in all sense similar to the reference listed drug, and one of the technique that is used is this UV far UVCD for secondary structure and the near UVCD for tertiary structure, right. So, near UVCD coming from aromatic amino acids, that includes disulfide bond and all those. So, if the far UVCD and near UVCD matches very well, you are sure that your molecule is very similar to the RLD molecule. So, here are 3 batch of a biologics drug. You can see batch 1, batch 2, batch 3, extremely overlapping, right. So, that is what it says, that the spectra says that although the protein is largely unfolded, because there is no characteristic peak of helix and sheet, it is a unfolded protein, but they are seeding, they are basically similar. The if you fit it little bit, it will get a beta sheet conformation, right. So, now if you look at the batch 1, batch 2, batch 3, here they are having some difference in the CD signal. It is a tertiary structure of 3 batches is different, secondary structure is not that different. That means, you have to still work upon this and make batch 1, batch 2, batch 3 similar, then only it will pass through it. So, this kind of extremely simple experiment tells you what can go wrong and what you need to fix it before you release the match. So, here there is no overlapping, absolutely overlapping signal in far UVCD, but in near UVCD it is not, there is a variation. Now, another application in biopharma can be from like a protein ligand interaction, right. We know all the time in drug discovery we want to have an enzyme substrate interaction, the receptor ligand interaction, ligand binding. So, all of these are possible to be detected through circular dichroism spectral analysis. So, if we record a spectrum and some changes is happening at 202 or 222, by monitoring the spectral signatures, you can find it out what kind of conformational change it happens. Not only conformational change, you can determine the binding affinity, the interaction kinetics and all so and so forth. So, CD becomes a valuable tool for investigating the dynamics of protein ligand interaction, right. You can continuously monitor the CD signal, what kind of changes it is happening and how you can quantify to get the KD like a binding constant of these proteins, right. So, one can like from the one can conclude the CD is extremely important non-destructive tool for UVCD, for protein secondary structure, alpha helix, beta sheet, random coil, tertiary structure, you can get it 250 to 350 because of this aromatic probes, and it gives you the fingerprint of 3D fold. Stability and folding, one can find it out TM, and you can compare and establish the biosimilarity, and also key advantage is that does not require too much sample preparation, no crystallization is required, concentration also can be very low, it is much faster than NMR and X-ray crystallography. Coming back to the main point for today's discussion is molten globule state. So, you see your protein is not all the time well folded, it can misfold, unfold, right. Now, molten globule state, if you remember your protein folding, molten globule state, it is a state that can be populated during the folding funnel, right. If you remember the concept of folding funnel, molten globule state is a compact, it is a partial molten globule as name suggests, melted and globular. Melted globular structure is called molten globule state, where the secondary structure remains contact, but third tertiary structures are loosely defined, right. So, the partially folded state where secondary structures are intact like alpha helix beta set remains intact, but it loses the tertiary structures, means hydrophobic interactions are exposed, and that makes the protein floppy or molten or melted, right. So, compared to fully folded state, your tertiary structures is melted, the hydrophobic surface are exposed, and that is a key intermediate in protein folding. And this provides the, if the hydrophobic surface are exposed, this provides the sticky surface of the protein in the environment. That sticky surface can attract the other sticky surface, and that is the initiation could be for protein aggregation or precipitation, right. So, this is molten globule state, it is between the folded state and unfolded state. It has still compact structure, high secondary structure content, but increase the surface hydrophobicity. So, molten globule state most of the time is in the equilibrium state of protein molecule, intermediate between their native state and unfolded state. These intermediates can be found in many protein with mild denaturation. So, if you have mild denaturation means if you are providing the urea 1 molar or 2 molar urea, it can be, we can populate the molten globule state, right. Moderately low pH, the high temperature or low concentration of urea and guanidinium chloride, we can populate molten globule state. Now, since this is a compact structure like a native structure, loosely packed non-polar cores are there, and it will be characterized by very high far UV-CD, but less pronounced the near UV-CD in this case. So, that is a native state, and here is molten globule state. If you look at many of the secondary structures are remain intact, but it is a different structure than the native state, right. So, what happens? So, suppose this is an enzyme, a very nicely active enzyme, and this for enzyme the residue in the core has to be correctly oriented, but in the molten globule state the structure is perturbed, although in your far UV-CD you look at same structure, but now the tertiary structure is lost, and therefore, enzymatic activity can go down. So, loss of enzymatic activity in spite of rigid tertiary structure, you can see if the protein is populating molten globule state, right. So, this means fluctuation in molten globule state are much larger than the fluctuation in rigid protein, because of the hydrophobic interactions are broken, and comparison of globular secondary structure of protein is important, and it has a relation to compact state of protein. So, such comparison would help to answer if the protein folding is correctly or if the enzyme is losing its activity, if we can identify these molten globule states, right. So, as we discussed, it is a folding intermediate, it works as a transient and stable structure during the protein folding pathway. What can be condition? Induced condition can be mild heat, low pH, some moderate denaturant condition. And relevance of this is important for understanding the protein folding, misfolding stability of protein. So, in food processing as well as studying the intrinsically disordered protein. Enzyme activity is lost, you can go and check it whether the protein tertiary structure is compact or has changed. So, this kind of significance this molten globule state can have. The important part is that structure is compact, roughly to 20 to 30% larger than the native state. Tertiary structure It has a loosely defined tertiary structure, dynamic structure. It lacks the specific unique interactions that are present in the tertiary structure. Secondary structure is largely intact and it resembles the native protein. Hydrophobicity, it increases the hydrophobic because hydrophobic interactions are losing. So, many of the hydrophobic residue are sticking out and that is providing a nice test bed for protein to aggregate. So, prone to aggregation. Environment, the frequent formed under stress condition like low pH, mild presence of denaturant and temperature. Right. So, here is my folded state and these are my molten globule state. Like if you look at most of the structures looks intact, but some structure has loosened out, that is the coil state. So, basically if hydrophobic surface area is exposed, how do you find it out? So, there is a dye called ANS. The ANS has a tendency to bind this exposed hydrophobic surface area and give rise to high fluorescence. So, typically in the experiment we find it out with ANS binding the protein is in molten globule state or not. That is a signature for molten globule state, that is a hallmark for molten globule state. Right. So, how CD can detect this molten globule state? So, one has to do the far UV CD secondary structure and you know secondary structure is intact. So, spectrum remains same, like you can see for presence of alpha helix 208 or 222 or beta sheet around 215 or 280 or a combination you can find. You can interpret that secondary structure remains same, well organized secondary structure similar to the native state. Now, key finding that amount of secondary structure in molten globule is often close to the native state, but important part is that tertiary structure is lost. So, if you do near UV CD, you see a collapse structure. Collapse structure, that means CD signal is not as much high as it was in your completely folded state. So, this actually reveals that the environment of aromatic amino acid is not the same. Tryptophan, tyrosine, phenylalanine, they were buried inside, now they are exposed. So, lack of sharp signal that you may have in the near UV CD and that has gone, and that says that it is a collapsed tertiary structure, the tertiary packing is lost. Right. So, key observation from molten globule state detection, secondary structure remains same, tertiary structure is lost and hydrophobicity, which we can prove with often with ANS, ANS a fluorescent dye that shows increased fluorescence and one can indicate that now hydrophobic surface area is lost. So, as I was mentioning to you that if we find this out, that means the function of an enzyme or protein can be greatly perturbed if the protein is going to molten globule state. So, how we find it out? Experimentally, say let us take a protein like cytochrome C or lactoalbumin in presence of low salt buffer at low pH like a pH 2, you can induce an acid unfolded or molten globule state, or in a buffer like a TFE or glycerol, one can populate this molten globule state. Then we do far UV CD, typically say we take a 0.02 to 0.1 cm cuvette and record the secondary structural spectra in far UV CD in this range 190 to 260, and we get like a molten globule shows far UV spectrum native like 208 and 222 minimum. Now, we do the same on same protein, the spectra we record in this near UV region, slightly you require a thicker cuvette and then you find that the spectra is weaker compared to the well folded protein, and that shows the loss of rigid specific tertiary structure packing. Actually, you can monitor the transition from native state to molten globule state. So, what you have to do, take the same protein, start adding acid to that. If you start adding acid, you see how the CD signal is getting lost at like if you in the tertiary structure, right. And you can do the data analysis, you can calculate the mean residue ellipticity, determine the amount of secondary structure in far and near UV CD, and one can find it out how much random coil is getting populated when the protein goes from native state to molten globule state. So, what is the experimental outcome? Where we have taken the lactoalbumin, we have reduced its pH to 2. So, what we found that at pH 2 lactoalbumin loses its tertiary structure, but retains large fraction of RUVCD secondary structure, indicating that classic molten globule state, tertiary structure lost, secondary structure intact. Cytochrome C, which was denatured using SDS, so like a mild denaturation. So, addition of low concentration of SDS or acid of cytochrome C, let us say at pH 2.2, pH 2, it shows a strong negative electricity at 208 and 222, indicating stable molten globule state. And if we take in acid salt condition, it forms a molten globule state where protein is compact, lacks the specific heme protein interaction in the native state, right. So, secondary structure remains intact, tertiary structure is lost. Now, BSA, one of the important protein, bovine serum albumin, alkaline induced, if you increase pH to 11.2, BSA exhibits a molten globule state. So, molten globule state is populated in different condition, and that is just one of the intermediate in the protein folding that can hamper the protein outcome. Similarly, like apomyoglobin at low pH around pH 4, it exhibits a compact intermediate, right, where the CD signal at 222 is high, but hydrophobic core is collapsed. Now, another protein like a human carbonic anhydrase at 1.5 guanidinium hydrochloride, it forms the well populated molten globule state, and that can be validated using ANS dye binding. Another protein, nuclear coactivator binding protein like NCBD, it again populates the molten globule state with a high alkyl content in its ligand free form and enables the flexibility at multiple partner. Another protein, apoflavodoxin, acid pH, basically it is from Helicobacter pylori, it forms the molten globule state at acidic pH, and that can also be characterized by compact shape, high secondary structure content and exposed surface area, which can be again probed by hydrophobic patch. So, what is the application of having this molten globule state? It is a first application is protein folding and stability. The folding pathway, one can CD can track the transition from native state to unfolded state by identifying the molten globule state, either by thermal denaturation or pH denaturation or chemical denaturation. So, folding pathway you can track it, you can track the stability, it measures the protein stability with temperature, pH denaturation, and one can find it out the ligand binding, right. It can detect the drug binding, what kind of a spectral change it brings, the ligand stabilizes or destabilizes the molten globule state and impact the drug design and folding pathway. Now, complementary technique, as we discussed, ANS is a very nice technique, ANS fluorescence is a very nice technique to detect the exposed hydrophobic surface area, that is a hallmark of molten globule state. Another technique you can do hydrogen deuterium exchange NMR, which determines which area is buried and which is exposed. So, if secondary structure is intact, lots of amide bond which is basically involved in secondary structure formation, they will remain unexchanged in molten globule state, but because of exposed hydrophobic area, some of these protons will be exposed. Another one, since the conformation has changed, the DLS can be used for finding the molten globule state. It is a slightly swollen structure, so you can find it out compared to native protein. So, what we can conclude that CD effectively distinguishes the molten globule state from the folded state, which has a random coil in far UV. The native state of protein shows native like secondary structure, but disrupted tertiary structure, and it is a signature for compact yet loosely packed molten globule conformation, and one can have application in a study the protein folding pathway, stability of a protein and ligand interaction, right. So, that is all for today, and let us continue discussion on CD in the next class. I look forward to have you in the next class. Thank you very much.